Okay, well, we lost the first hour. Here's the second hour. Yeah, enjoy it. All right, so we'll try that again. Okay, so how about one more by parts, just for fun? What about the integral, whoops, of e to the x cosine x? How about that? Yeah, I know, shut up. Um, so, Long Island Pet says u is e to the x, so exponential over trig. Et, right? Exponential is better than trig. All right, so let u equal e to the x. I don't think there's a tic-tac-toe, so don't worry about that. And dv equal what? Cosine x dx. Good. So what's du? E to the u dx. Oh, sorry, e to the x dx. What's v? Sine. I remember the derivative of the cosine is negative sine, but the antiderivative of the cosine is sine. So what do you get? What times what? E to the x times sine x. Good. Minus the integral of who? E to the x sine x dx, right? In other words, u times v, that's this, minus the integral of v du. There it is, the integral of that. I wrote it this way. Wait, I thought the idea was to get something I don't know how to integrate into something I do know how to integrate, but I don't know how to do that either. I'll do it again. You know what? I'm going to do that on a separate page, all right? So what's this then? Right? We started with e to the x cosine. We need e to the x sine, right? All right, let's do that again. So who's u? E to the x. Who's dv? Sine x dx. So who's du? E to the x dx. And who's v? What? Negative cosine. Remember, the derivative of the sine is cosine, but the antiderivative of the sine is the opposite of the cosine. So what do you get? What times what here? Let's start you off. E to the x times negative cosine. Right. Minus the integral of what times what? Negative cosine times e to the x dx. Well, if I do negative cosine e to the x dx, it's negative, but I'm subtracting a negative, so I'm really adding it. Wait a freaking minute. What? I start with e sine, I get e cosine. I start with e cosine, I get e sine. I wanted e cosine, and guess what? It's there again. Huh? Is this a problem? No, it's not. Look at the signs. Not the S-I-N-E, the S-I-G-N. Watch. The antiderivative of e to the x sine x dx is this mess, right? I'm going to replace it for this. And take this and replace it. Subtract that stuff. How do you subtract the negative? You add a positive. How do you subtract the positive? You add a negative. So this is positive, this is negative when I subtract it, right? Okay, so let me rewrite this. This initial, whoops, wrong way. The initial problem, I'm going to rewrite it. I'm going to say it's e to the x cosine x dx equals this stuff, e to the x sine x plus, because I'm subtracting this negative, e to the x cosine x, e to the x cosine x, and then I'm subtracting this positive, so it becomes negative, the integral of e to the x cosine x, okay, minus the integral of e to the x cosine x dx. Why is this good? This is weird, but it's good. We haven't seen this yet, but it's good. You see this? You see this? They're the same, right? Except for this. I'm trying to solve for this. Can I put them together? What if I add this to both sides? No. This is subtracting here. I'm going to add it. So I get 2 of these equals this. And just divide by 2 to get what you wanted. Ta-da. So sometimes what it does is it cycles. It cycles back and forth between sine and cosine, sine and cosine, sine and cosine. As long as you end up with that negative, what you started with, you can just recombine it and you're good. And so that's a special case of by parts. That happens rarely, but you should be familiar with that. Okay. All right. So any questions on by parts?
We can do this by the column to one thing.
Yeah, I guess you could. It may not be obvious that things, combine, but
So when, so we get whatever you get the first one again.
well, you could always do this as a column. It's not going to be tic-tac-toe. It's going to be tick or tic-tac. You could always do column if you want, but it might be a very short column. Yeah, that's fine. Okay, so now that's a little weird case, but be aware that happens. All right, I think we've got to move on. Now, notice I'm skipping 7.3, integration tables. Why? Because if you combine all the antiderivatives you know with u sub by parts, and what we're going to do in a minute, partial fractions and trig substitution, you don't need any freaking trig tables, okay? Everything in a trig table, that which someone else already did a lot of antiderivatives for you. You don't need that, okay? So I don't do 7.3, skip that. All right, so here we go. How do you integrate quotients? That's what we're talking about now. That's 7.4. Let's say I want to integrate this. It's a good example. All right, there's a quotient. So it's sort of like like a quotient rule. If the degree of the denominator is greater than or equal to the degree of the numerator, you can use what's called partial fractions, okay? What's the degree of the denominator? If you FOIL this out, what's the highest degree? Second degree, 2, right? What's the degree of the numerator? Technically, there's a 1 here. What's the degree of a constant? 0, because isn't that 1 times x to the 0, right? That's a 0 degree. If you FOIL this out, you get what? X squared minus 7x plus 10, so it's second degree. So if the denominator is a higher degree or equal degree to the numerator, this is probably a good way to go. All right, here we go. What you do is you don't integrate this. You break it up. You say, okay, forget calculus for a second. This is algebra. Can I rewrite this fraction in a simpler manner? Okay? And from linear algebra, we have this thing called partial decomposition that says, if the denominator is factorable, you can break it up as a sum of 2 fractions with those denominators, with those factors as denominators. Okay? Now remember, this has to be a higher degree than this, or equal to it. This does too. What degree is this? First, so I'm going to make this 0 degree, some number, A, I don't know what it is. What degree is this? First, I'm going to make this 0 degree, some number, I don't know, B. Can you figure out what A and B are? You know what's nice about this? Say, for example, A is 1. Don't you know how to integrate 1 over x minus 2? dx. Instead of integrating this, you're going to integrate 1 over x minus 2 dx. Isn't that ln? So you're going to make this something that you can't integrate into something you can, involving ln's or something. Okay? So this is algebra now. This is not calculus. How do you get A and B? You need a common denominator. How do you add 2 fractions with different denominators? Get a common denominator. These denominators are relatively prime. They don't have any factors in common. So all you do is multiply them together to get a common denominator, right? So what do you multiply top and bottom by to get a common denominator? X minus 5. And here? All right, so multiply this by x minus 5. Ax minus 5a. Multiply this by x minus 2. B, whoops, that's not a B. Bx minus 2b. Plus, has to equal 1. Notice, I'm not worried about the denominators anymore because they're in common. How to make these fractions equal? If the denominators match, I've got to make the numerators match. That's the numerator here. That's the numerator here when you combine the denominators. Okay. Doesn't this give you an equation? 2 equations for A and B? Remember, if you have 2 variables to solve for, you need 2 equations that are linearly independent. Didn't we do some of those at the very beginning? Look what this is saying. This is a constant. Is that a constant term? This is 0 degree term, right? Is that a 0 degree term? No, that's a first degree term. There's a 1 here. Is that a 0 degree term? Yeah. Is that a 0 degree term? Is that a 0 degree term? Well, that's supposed to be minus. Right? That's a 0 degree term. That's a 0 degree term. They have to combine to 1. All right, let's write that. Let's see. Negative 5a minus 2b equals 1. Okay. What about the linear terms, the first degree terms? ax plus bx equals, well, how many x's do you see? None. Right. So where is it now? A x's plus b x's is 0. How do you solve those two equations for a and b? Any ideas? Well, we talked about this. Elimination, substitution, graphing, matrices. Well, actually, you didn't know matrices, right? Linear algebra. No? Well, you could solve for A in terms of B and plug it back in and find A. Or can you cancel stuff? Is there a way like you can cancel the B's? So you can only deal with the A's at, one variable at a time. How would I get these to cancel? If I had a 2 here, we could combine them and they would cancel, right? How would I get a 2 here without changing the equation, really?
Add 2 to all of them.
Not add, multiply. Let's multiply everybody on the bottom by 2, and I'm going to get negative 5a minus 2b equals 1 and is not changed. Then I got 2a plus 2b equals 2, actually, right? And what are you going to do? Add or subtract these two equations to cancel out the b's? Add. So combine them. How many a's do you get? Negative 3a. This cancels, equals 3, right? I'm adding. So if negative 3a is 3, what's a? How do you get a alone? Divide by negative 3 into 3, you get negative 1. Okay. If a is negative 1, what's b? So it adds up to 0. If a is negative 1, what's b? 1. Okay. You just solve two equations with two unknowns, a and b. Okay.
Multiplying 2 times 0, isn't that just be 0?
Well, that's a 0. Wait, I'm sorry. I was looking up here. Thank you. I multiplied this guy. Dang it. 2 times a, 2 times b, and 2 times 0. Sorry. Whoops. Hang on. This is 0. Huh? Sorry, what? Oh, okay. So when you add these, you get that. When you add these, you get that. When you add these, you get 1. Sorry. Good call. So a is negative 1/3. If a is negative 1/3, plug it back into either equation. I don't care, but this one's easier. If a is negative 1/3, what's b? Positive 1/3. Okay. Yeah, that changes it a little bit. All right, so a is negative 1/3. B is positive 1/3. I'm going to rewrite the integrand. I'm going to say, okay, integrate negative 1/3 of 1 over x minus 2 dx plus positive 1/3 the integral of 1 over x minus 5 dx. See what I did? I just put negative 1/3 here, I put positive 1/3 here, and I put the integration symbols back in. That's all I did. Okay, I put this up here, but a is negative 1/3. I put this up here, but b is positive 1/3. Okay, so now you know how to integrate this, right? What do you get? What's the antiderivative of 1 over x minus 2 dx? ln. If, in other words, if u is x minus 2, du is dx, right? So this is 1 over u du. How do you integrate 1 over u du? ln u, right? Okay, wait. Let's move this to the next page. I got this. So we got the integral of 1 over x minus 2 times x minus 5 dx is negative 1/3 the integral of 1 over x minus 2 dx plus positive 1/3 or plus 1/3 the integral of 1 over x minus 5 dx. Now this is technically a u sub, but it's a straight u sub. It's not one where you have to multiply divide by 2 or something. If this is u, isn't that du already? If u is x minus 2, du is dx, right? So do you even have to write this out? It's a u sub? It's a u sub, but you don't have to write it out. This is going to be negative 1/3 the ln of absolute x minus 2 plus what? 1/3 the ln of absolute x minus 5 plus c. That's the answer, but you might factor out the 1/3, and you might rearrange the difference, and you might write it as 1 ln. That's just playing games with ln's. This is an answer. You can leave it like this, but this is equivalent. Okay? What do I do? If I took out the 1/3, then this is still negative. I'm thinking, that means I'm subtracting, right? So I just swapped it. This is still negative. This is still positive. I didn't change any signs, right? I just moved it. And then remember that the difference of two logs is the log of the quotient. The difference of two logs is the log of the quotient of the arguments of those two logs, right? So that's an answer, that's an answer. Either way, that's integration by partial fraction. Yeah.
I understand. Can you explain to me again the purpose of the A and B?
To make it so that this is easy to integrate, because you're breaking it down into simpler fractions.
What is the A and B?
They're just some constants.
Just constants.
They're just, in this case, they're always just constants. Yeah. There might be an A and a B and a C, but they're all at constants. Okay? All right, let's practice that out. Let's play with that. Let's see, what can we do for that? All right, how about this one? What's the antiderivative of x plus 2 over x squared plus x? Is this a candidate for partial fractions? In other words, is the degree on the bottom greater than or equal to the degree on the top? Yes. Also, is the bottom factorable? It's not factored yet, right? How do you factor it? Put out an x, GCF. So you get the integral of x plus 2 over x times x plus 1 dx. Now stop there with the calculus and go do some algebra. How do you break this up? First of all, how many fractions do I write? Since there's two factors, there's two fractions. What's this denominator? What's this numerator? A. What's this denominator? What's this numerator? How do you figure out A and B? Get common denominators. Multiply top and bottom by x plus 1. So ax plus a plus, what happens here? Well, so you bx. Okay, that's an a. Is equal to x plus 2. So 2 has to match the 0 degree term, right? And x has to match the first degree terms. So right away I get that a is 2. A is 2. That's nice. Right away, a is 2. Free. I got a for free. This 0 degree term matches this 0 degree term. There's no other 0 degree terms. Last time I had an a plus a b or something. So it was a little more complicated. But now, notice that I have ax plus bx is 1x. So a, what does that tell me about a and b? A plus b equals 1. If a is 2, I know that a is 2 already, right? If a is 2, what's b? -1. So a is 2 and b is -1. We okay? Okay, so now what that lets me do is, it lets me rewrite this way, where a is 2 and b is -1. All right, so let's do that on the next page. Any questions up on here? Okay, because there are ax's plus bx's. Remember, when you add algebraically, you can all add like terms, right? So ax has to combine with bx, but it has to match 1x, because it's got to be equal. Remember, when we got the common denominators, the denominators matched. How do we make the fractions equal? The numerators have to match. So this numerator has to equal that numerator. So a is 2, and a plus b is 1. Gotta be. No choice. Okay? All right. So let's rewrite this question in terms of what we just found. This is called partial fraction decomposition. That's an algebraic technique you should have seen in pre-calc. No? Does that sound familiar at all? Yeah. All right, so I'm going to rewrite this. I'm going to say, okay, the problem was the integral of x plus 2 over x squared plus x dx can be rewritten as the integral of a, which, well, what the heck was it? 2, right? A is 2 and b is negative 1, right? A, which is 2 over x, plus a negative 1, right? So minus the integral of 1 dx over x plus 1. So there's a dx here, there's a 1 dx here. All I did was I put in the 2 and the negative 1, and I put the integral and the dx back in. I put the integral and the dx back in. Okay? Now this is nice because what's this antiderivative? You should know it. I'll start you off. 2 ln absolute x minus what? Ln absolute x plus 1 plus, don't forget, c. That's an answer, but some people like to do this. Probably Bob, by the way. And end up with this. And that might come in handy to play around with the LNs that way. But this is an answer. You can stop here if you're like finding an area or something. Right? If you're doing the area from 0 to 1, you can plug in 1, you can plug in 0, whatever. Right? Okay, this is terrible. Yeah, I know. But you're getting the idea? Let's practice some more. But you're getting the idea, right? Okay, practice some more. How about this one? Can I move on? Okay. This is a shame. I'm cheating you with the first hour. Oh, well. Whatever. All right, remind me. No 89s or 92s. Again. No right clicks, especially with this. Again. That's what killed Monday last week, remember? I think that's what it was. Okay. Anyway. I've used this thing all year long. In a different environment, but all year long. Never had that problem. This is really bugging me. But anyway, let's say, all right, this is what we want to integrate. Let's integrate 2x squared minus x minus 1 over x squared plus 1 times x minus 2. All right, so it's already factored for you. Is it true that the degree of the denominator is greater than or equal to the degree of the numerator? Okay, so partial fractions is probably a good way to go. All right, so no calculus anymore. Now we rewrite this, okay? We're going to say, all right, 2x squared minus x minus 1 over x squared plus 1 times x minus 2 can be rewritten as how many fractions? 2. 1 with this denominator, and 1 with this denominator. Now remember, this is first degree, so this has to be 1 less. What? First degree, what degree? 0. That's just a constant, right? So careful, this is second degree. So this has to be first degree. Isn't that first degree? So now you got to figure out A, B, and C. To figure out a solution for A, B, and C uniquely, you have to have 3 linearly independent equations in 3 variables, which in 3 space corresponds to 3 lines, not necessarily in the same plane, that intersect in 3 dimensions at one point. Aha! How do you do that? Well, it's not that bad, actually. How do you get a common denominator here? Multiply top and bottom by x minus 2. Multiply top and bottom by? Okay, so do so. It's going to be bx. Yeah. It's going to be bx plus c times x minus 2 plus, oh, I could write it out, ax squared plus a. I really need to FOIL this out, right? All right, so FOIL this out. You get how many x squareds? Do FOIL. First, outer, inner, last. Double distribution. So, bx squared, then minus 2bx, then plus cx, then minus 2c plus ax squared plus a equals 2x squared minus x minus 1. All right, so do you see in here anything that matches a constant or 0-degree term here? That's second, that's first, that's first. No, there you go, that's a constant. That's second, oh, there's a constant, right? So what does that say? A minus 2c equals negative 1. That's right there. A minus 2c equals negative 1. All right, forget the constants now. I did that, I did that, I did that. How about the linear terms? Negative 1x, right? So negative 1 equals what? Let's see, where's the linear terms? Negative 2b plus c. Is there any other linear term? Anything else that says x? That matches x, right? So I got negative 2b plus c. Okay, negative 2b plus c equals how much? Also negative 1. Right? That's this negative 1. Yep. All right. And then what about the 2? 2 equals what?
The x squared.
The x squareds. But don't worry about the x's, just the numbers, the coefficients. 2 matches the b plus a. All right. So a plus b. Aha. How do you solve 3 equations, 3 variables? Yeah. Any ideas? Same way as before. Eliminate stuff. Try to do it. Try to get it so that you can cancel out the A's, cancel out the B's, figure out C, plug it back in, cancel out B's, figure that out, plug it back in. Aha. But there's an easier way. This takes a lot of paper. Do you have a lot of paper left? No, hopefully not. All right. So this is what you do. You invoke what you know about matrix algebra. You know about matrices, right? Never did matrix? Ever heard of a determinant? Ever hear of a 2x2, a 3x3, a 2x3 matrix, stuff like that? Well, you're going to hear about it right now. This is hard to do by elimination, so I'm not going to do it that way. All right, let me just copy this over for a second. It's a minus 2c is negative 1, right? So a minus 2c is negative 1. And it was negative 2b plus c is also negative 1. Negative 2b plus c is also negative 1. Negative. All right. And a plus b is 2. A plus b is 2. You can rewrite this as a matrix this way. Are you ready? Notice that there are 3 equations and 3 unknowns. I'm going to make a 3 by 3 matrix, simply including the coefficients. How many A's? 1. How many B's? 0. How many C's? Negative 2. How many A's? 0. How many B's? Negative 2. How many C's? 1. How many A's? 1. How many B's? 1. How many C's? 0. Times A, B, C equals negative 1, negative 1, 2. Okay, now what does this mean? This means I'm solving a matrix of known numbers times an unknown equals some other matrix of known numbers. Now, forget that it's a matrix for a second. If I said AX equals B, and it's just plain numbers, how do you get X alone? Divide everybody by A, right? But you can't divide by matrices because they can represent vectors. And of course, when you did vectors in physics, you added them, you subtracted them, you multiplied them, you never divided them, did you? You can't divide by a matrix. But you can multiply by the, what's the same thing as dividing? Multiplying by the reciprocal. So X, the solution matrix, what is A, B, and C, is A inverse times B. The only thing you really don't understand here is how do you multiply a matrix by a matrix? When you multiply a 3 by 3 matrix times a 3 by 1 matrix, you get a 3 by 1 matrix. This works. What the freak is he talking about? You've never seen, no, has anyone seen anything like this? Okay.
Saw a matrix.
Okay. The movie? There were three of them, right? Yeah. With that, what's his name? What's his freaking name? Keanu Reeves, right, yeah. The first one was okay, but then it gets tedious. All right, anyway, so this is it. Look, what am I saying by 3 by 3? 3 rows, that's this 3. 3 columns, that's this 3. 3 rows, 1, 2, 3, that's this 3. 1 column, right? Now, when you multiply a matrix times a matrix, these two numbers have to match. And they do. And if these two match, what you get is this big, 3 by 1. 3 by 1. That's good. Why? How do you do it? Did you ever multiply two vectors, what do they call it? A scalar, the dot product. You ever do the dot product of two vectors? That's what this is. To get this piece, you take this row vector times this column vector. Do you know how to do a dot product? 1 times A plus 0 times B plus negative 2 times C has to be negative 1. Isn't that what I said up here? 1 times A plus 0 times B plus negative 2 times C has to equal this piece, negative 1. This is just a restatement as one matrix equation of these three equations. Look, if I multiply this row vector by this column vector, I get this equation. 0 A's plus negative 2 B's plus 1 C has to equal that component. You ever do vectors in 3 space? It's like an X, a Y, and a Z, or an I, a J, and a K vector? No, nobody knows. Okay. All right. Multiply this row vector by this column vector as a dot product or a scalar product. 1A plus 1B plus no C is 2. This is the same as this. Now, if you can write this, you can copy this, yes? This is easy. The rest of the calculator does it. You make this matrix on the calculator, you make this matrix on the calculator, you type this, you're done. Okay? The key is, can you write this? Can you write this based on that? It's just copying the numbers over. Okay, I'm going to now call on Ziggy, which crashed, so it's not here anymore. So let's call on Ziggy. And not Hal. Hal is evil. Hal is always crashing everybody. Well, actually, it was a 92. That's Colossus. Sorry, that's another story. All right. Let's bring up... Where did he go? There. Okay, so here's, let's get E3. All right, so I'm going to go into the matrix menu. Do you see the matrix button on your calculator? Now, on some calculators, the 83 plus or the 84, it might be somewhere else. Sometimes it's down, it's over here, like second math or something, or second angle or something crazy. But I have an actual matrix key. Do you see it? Do you have to do a second? Is it yellow? Okay, do the second, whatever, okay? So hit matrix. Now you can actually fill in matrices, okay? I'm going to go over to edit, A, so enter. And how big is it? 3, this guy here, right? How big is it? 3 by 3, so that's what's right. 3, enter, 3, enter. So now there's space to type in all the numbers. And since it's in fixed 4, it's got all those decimals, but I don't need them because these are all exact numbers. So just type. I'm copying this matrix over in row echelon order. In other words, top row first, from left to right. Second row from left to right. Third row from left to right. So 1, enter. 0, enter. Negative 2, enter. Okay? 0, enter. Negative 2, enter. 1, enter. Okay? 1, enter. 1, enter. 0, enter. Done. Okay? So matrix A is stored. Remember, as soon as you type stuff, it's automatically stored. There's no, like, save key, right? Like in program mode, same thing. All right, go back to matrix. Now what do you think I'm going to do? I defined matrix A. I'm going to define matrix B. So go to edit, 2, enter. How big is it? 3, enter, 1, enter. Okay. What do you type? -1, enter, -1, enter, 2, enter. Because that's A, that's B, that's this. I just copied this. Okay, now the calculator does everything. You ready? Do second quit to get out of the screen, to the home screen, right? You might clear stuff. All right, I just typed in this. Okay, you ready? It's matrix 1, or A, inverse, times matrix B, or 2, enter, enter. Is it all one? It is? Oh, good, okay. I didn't think it was going to be all ones. It's a fluke. It's not always all one. Sometimes it's crazy numbers, okay? Sometimes it's negative, sometimes it's a half, sometimes it's right, sometimes it's fraction. It's okay, but it just turned out to be all ones. Okay, fine, so that's nice. That's easy. Are you okay? Now look, Ziggy did all the work. To actually do this by hand involves matrix determinants and Kramer's rule. Anyone hear that? No? Don't worry about it. Ziggy does it. Okay, so let's go back to what we were doing. What the hell were we doing? Well, we needed A, B, and C. We figured out what's A, B, and C. That's it right there. That is X, which is the answer you're looking for. A, B, C. A is 1, B is 1, C is 1. Do you see where I'm getting what A, B, and C are? Okay. So what did I want to do with that? Well, I wanted to fill that in here. Right? So this is 1x plus 1 over x squared plus 1 plus 1 over x minus 2. Okay. So let's rewrite the problem. Okay? What were we doing? We were doing the integral of 2x squared minus x minus 1 over x squared plus 1 times x minus 2 equals, now remember we said bx plus c was 1x plus 1 over x squared plus 1, right? Plus, what was it? A over x minus 2, and a was 1. Now I'm just going to put in the integrals and the dx's again. Integral, dx. Integral, dx. Now you can integrate. Can't you? Let's see. Let's start here. What's the antiderivative of 1 over x minus 2 dx? ln of absolute x minus 2. What is this one, though? That's not so obvious. If u is x squared plus 1, that ain't du. But wait, it's not that bad. You could, but you don't have to. Look at this. Is that the same thing? Sometimes it's easy just to break it up, and you don't have to do another partial fraction. You can't actually do partial fraction here because it's not factorable. This isn't factorable, right? Okay. This you can do, this you can do, this you can do. You forgot. This is ln absolute x minus 2, right? This one you forgot, didn't you? We derived this one. We had somewhere along the line something whose derivative was 1 over 1 plus x squared dx. Do you remember? Something whose derivative was 1 over 1 plus x squared. Let's leave it at that. Not tan, close. Arctan, yeah. So the derivative, we figured this out way back somewhere. The derivative of the arctan of x is 1 over 1 plus x squared. So the antiderivative of 1 over 1 plus x squared dx is arctan. How do you do this one? This is a u sub. U is? If u is x squared plus 1, du is 2x dx, right? So you're going to replace x dx with what? 1/2 du? And this is, you're going to replace this with 1/2 du. You're going to replace this with, what is x squared plus 1? U. So you got 1/2 1 over u du. How do you integrate 1 over u du? ln absolute u, but u is, and there's a half in front. So again, 1/2 the ln absolute x squared plus 1 plus arctan of x plus ln absolute x minus 2 plus c. That's it. That's what you get. Okay, so sometimes you notice there's one quotient rule for differentiation, but there isn't one quotient rule for anti-differentiation. When you get a quotient that you're anti-differentiating where the degree of the denominator is greater than or equal to the numerator, this is third degree, right? This is second degree. You do the partial fraction stuff, but notice what you end up with. This is sort of a quotient rule for anti-differentiating involving ln. This is sort of a quotient rule for anti-differentiating involving arctan. And if you use u sub here, you get ln again. So a lot of times when you do the partial fractions, you end up with ln's and arctans, arcsines, crazy stuff. Okay?
So the tan was anti-ln?
No, that won't work, because if you take a look at, look at it again, if this is u, this is du, you don't have x dx. There's no way to substitute something for dx and get rid of all the x's. That's the problem. If you did this here, it wouldn't work. All right, so this is ln, this is arctan, this is a u sub, then it's an ln. That's about as nuts as it gets, except for trig sub. Aha, there's more. Okay, let's, for example, prove that this is the arctan. Let's say you don't remember that. I have a way to prove it, another way. Let's say trig sub. This is a good trig sub. Okay, let's do this. Let me think about this. Hang on. All right, let's do this. Let's show that this is the arctan using a new technique. This is the fourth technique now. We did u sub by parts, partial fractions. U sub, the opposite of the chain rule. By parts, the opposite of the product rule. And partial fractions is sort of like a quotient rule thing, right? Here's a new thing, trig sub. If it's not integrable this way, it might be easy to integrate using some trig substitution, okay? Think of what you know about right triangles, Pythagoras and stuff. Can you draw a right triangle such that this is one of the sides? The 1 plus x squared. Where would it be? Would it be the hypotenuse? Would it be one of the legs? Think about it. If it's one of the legs, usually there's a square root involved. Well, actually, that's not... All right. Usually there's a difference involved. Look, what if I say this is x and this is 1, for example? What's this according to Pythagoras? What does Pythagoras say? A squared plus b squared is c squared, right? So x squared equals 1 squared plus stuff. So how do you get the stuff? Well, the stuff, let's call it b. B squared. How do you get b? Subtract the 1. And then square root, right? So there's a radical and there's a difference. I don't have a difference. So that's not a good choice. How do you get this as one of the sides? I don't want a minus. I got a minus before. Where would you put the x? I put it on the hypotenuse already. It didn't work. Put it somewhere else. Now, what's c? A squared plus b squared is c squared. C squared is a squared plus b squared. So c is rad a squared plus b squared. There's the x squared plus 1. There it is. Okay. Or 1 plus x squared if you like. Same thing. Okay? So this is what you're going to do. You're going to now invoke some trig. If this is theta, the angle theta, forget this for a minute. What's the relationship between theta, x, and 1? Soka-toa, east of Jawa. You forgot already. So-ka-toa. What do I got here? From this angle, that's the Opposite, that's the adjacent, so I'm doing tangent, right? So that means the tangent of theta is x over 1. Okay. So wherever I see x, I'm going to put tangent. Wherever I see x, I'm going to put tangent. It's sort of like u sub. I'm substituting stuff. But instead of ending up with u's, I'm going to end up with thetas. All right, I need a substitution for dx. Well, if x is tan, what's dx? Secant squared. Theta d theta. All right, so where I see dx, I'm going to write that. Dx is in the numerator, that's it. Secant squared theta d theta. Over 1 plus x squared. Well, this is x. So that's x squared this, you get x squared. And that looks worse, doesn't it? But it isn't, because it's actually very simple to simplify. Do you know your Pythagorean trigonometric identity that says 1 plus tan squared is what? It happens to be secant squared. Did you know that? Uh-huh. You used to. Well, now you do still, because this one everyone remembers, right? What? 1. What if I divided everything by cosine squared? Sine squared over cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. 1 divided by cosine squared is secant squared. It's the same rule as that. If you remember that, you know this. What if I divide everybody by sine squared up here? Sine squared over sine squared is 1. Cosine squared over sine squared is? Well, you know sine over cosine is tangent, so cosine over sine is 1 over tangent, but that's also known as cotangent. And the 1 over sine squared, if 1 over cosine squared is secant squared, 1 over sine squared is cosecant squared. These trig identities, these are the Pythagorean trig identities, come in handy. So tangent squared of theta plus 1 is the secant squared of the same theta. Tangent squared plus 1 is secant squared. All right, so I got the integral of secant squared theta, d theta, over secant squared theta. What happens? What do you want to do? You're going to cancel what? Secant squared. What's the antiderivative of d theta? Come on. Theta plus c. Wow, that was hard. But who's theta? If x is tan theta, how do you get theta alone? How do you get rid of tan? What's the opposite of tan? The inverse tan. If I arctan both sides, theta is the arctan of x. So theta is the arctan of x. So if you didn't believe it before, this antiderivative is the arctan. There it is. Okay? All right, so that's called trig sub. It's rewriting it so that if it's not integral the way it's written, maybe it's integral in terms of some kind of a trig substitution, some kind of thing in theta. Okay? All right. Try this on for size. What's the antiderivative of 1 over rad 1 minus x squared dx? Now, you drew a right triangle before that had 1 plus x squared. And by accident, we had the 1 minus x squared, right? Didn't we? Where was the 1? Where was the x? So you end up with minus here. So that one of the legs involves this denominator. There's a lot of... Huh? Where would you put the x? Where did we have it when we got the minus? Hypotenuse. You can put the 1 wherever you want. I'm going to put it here. So what's this? If I call this a squared, b squared, c squared, how do you get a? A squared plus, this is Pythagoras, a squared, b squared, c squared. A squared plus 1 equals x squared. So a squared equals x squared minus 1. Oh, wait, that doesn't work. That's if I wanted x squared minus 1. I want 1 minus x squared, right? We got this before, but that's not what I want. So fix it, quick, hurry. Switch these two around, right? Okay. If I put the 1 here and the x here, then I'll get what I want, because that's not the same as this, remember? Okay, so let's fix that. So a squared plus x squared equals 1. A squared plus x squared equals 1 means that a squared is 1 minus x squared. So a is rad 1 minus x squared. So this side is identically that denominator. That's good. I'm going to write that. So now let's do the theta thing again. Forget this for a minute and worry about what you place, the 1 and the x. Is there a relationship between theta, x, and 1? Salkatoa, which one? Sine, cosine, or tangent? Opposite over hypotenuse is sine. Right. Okay. So the sine of theta is the opposite over the hypotenuse, x over 1. Okay. So wherever I see x, I'm going to write sine. What do I write for dx? Dx is the derivative of this, cosine theta d theta. So where I see dx, I'm going to write this. Where I see x, I'm going to write this. Okay. So dx is cosine theta d theta. That replaces the numerator over the square root of 1 minus x squared, but x is sine. Okay. But what is 1 minus sine squared? Wait, go back. What is 1 minus sine squared? It's cosine squared. If I move sine squared over, right, I get cosine squared. Okay. So this is the integral of cosine theta d theta over the square root of cosine squared. But what's the square root of cosine squared? Cosine. And what's cosine over cosine? 1. So again, you're integrating d theta. So what do you get? Theta plus c. But who's theta? If sine theta is x, what's theta itself? The inverse sine. Arc sine both sides. And you get arc sine of x plus c. So this antiderivative is arc sine, and the derivative of the arc sine is that. By the way, did we ever say the derivative of the arc sine? There it is. The derivative with respect to x of arc tan is 1 over 1 plus x squared. The derivative with respect to x of arc sine is 1 over rad 1 minus x squared. That's what it is. We never did that one, but there it is. And so the integral of this is that, and the integral of this is that. The integral of 1 over 1 plus x squared dx is arctan. And the integral of 1 over rad 1 minus x squared dx is arcsine. We knew this, but we didn't know that. Alrighty? So, alright, we've got 5 minutes. What's a good example there? All right, here's one. Here's a good example. Here's one more. So let's do one more, and then we're done for today. Okay. All right. I'm still ending at 9:15, even though I gave you an extra little break. Okay. Just because you're so nice. All right. What if I want to anti-differentiate 1 over x squared plus 9 dx? Can you write a right triangle where one of the sides has this in it, with or without a radical, doesn't matter. By the way, notice you can't use sub this. You can't partial fractions this because it's not factorable. It has to be factorable. Remember, we break it up based on factors.
Can't do x squared plus x squared?
No. Try it. FOIL it out. It doesn't equal x squared plus 9. It gives you x squared plus 6x plus 9. Yeah, you can't factor. So it's not a partial fraction. It's not a u sub. It's definitely not by parts. It's by parts. It's products. That's not a product. So when all else fails, trig sub, right? All right, so where are you going to put the x? Would it go in the hypotenuse or one of the legs? All right. And then where are you going to put the, well, is it a 9? It's a 3. Where do you want to put it? Well, I guess either leg, it doesn't matter, really. Okay, 3. So what's A? Does it look like this? No, it doesn't. Look. A squared plus 9 equals x squared. A squared is x squared minus 9. That's bad. I want plus. Not a good place for your x, not a good place for your 3. So forget that. Put the x somewhere else. Where? One of the legs, okay. Whoops. Where are you going to put the 3? Another leg, right. If you put it here, it's going to get minus again. Put it here, you're going to get plus. Okay, so let's say, what's C, just to see if it works. A squared plus B squared equals C squared. So let's do it this way. A squared plus B squared is C squared. X squared plus 9 is C squared. There you go, that's what you wanted. So C is rad that, right? Okay, so this side is rad x squared plus 9. So you got the x squared plus 9, that's the point. But what's the relationship between the angle and those two sides you placed? So Katoa, which one? Tangent. The tangent of theta is opposite over adjacent. So tan theta is x over 3. I need x. How do you get x alone? Multiply by 3. All right, so let's just write it that way. I also need dx. What's dx? Differentiate this. What do you get? 3 what? Derivative of the tangent, remember, is secant squared. We figured it out using the quotient rule of sine over cosine. All right, so let's replace stuff. This is sort of like U sub where you're replacing everything. So all the x's go away, and you just end up with thetas, okay? So dx, that's this, integral of 3 secant squared theta d theta, over x squared, that's this, 9 tan squared plus 9. Okay, so now what? How do you simplify this? The point is that hopefully this simplifies to something you can integrate. Last time everything canceled out. I don't know, it doesn't always all cancel out. You can factor out a 9. Okay, so I'm going to get, there's a 3 on top, secant squared theta d theta. There's a 9 on the bottom, times, factored out, tan squared theta plus 1. But remember, didn't we just say tan squared plus 1 is what? Secant squared. Aha. So that, well, what's 3/9, by the way? 1/3. I'm going to pull that up. 1/3, the integral of secant squared theta d theta over secant squared theta. What happens with the secants? They're all gone. So you get 1/3, the integral of d theta. Well, that's one of the easiest integrals there is, isn't it? You get 1/3 of what? Theta. But, again, what's theta? Remember, we originally wrote it this way. If the tangent of theta is x over 3, how do you get theta alone? Inverse tan, both sides. So, what do I write? The arctan of what? I arctan both sides. What did I get? X over 3. Don't forget, over 3 plus c. That's it. All right, so U substitution, by parts, partial fractions, trig sub. Practice for homework. We're done. Unless there's any other questions, let me know.